Okay, hello everyone. I would like to welcome you on our first of the series of webinars based around reaction calorimetry. My name is Prchal. I work with a UK-based company Syrris, and we make a lot of chemical devices. So, just to keep the introduction short, I will firstly talk a little bit about Syrris because some of you may not be familiar with us. So, what do we do? And then we will move on to the main topic, which is the reaction calorimetry. So Syrris, we actually are a fairly old company in the business. We celebrated 17 years on the market. We were founded in 2001 to address the challenges faced by pharmaceutical industry, which were mostly at the time availability of the flow chemistry or continuous processing systems. So we are actually the longest established flow chemistry company on the market. And you can find our equipment, not only flow chemistry, but even batch chemistry reactors all over the world. We actually have a global reach on markets. We are headquartered in the UK, in Royston near Cambridge. We have around 125 people working on site, and we have offices all around the world. As I said, we have offices in the United States, Japan, India, and newly opened one in Southeast Asia in Vietnam. And we have a quite extensive network of distributors as well. Syrris itself is a part of the Black Trace group, so we actually focus on more fields. So we have a few sister brands. I will keep this very short. If you're very interested, please have a look at our website and you can find more information. So just to keep it short, Dolomite is a sister brand focusing mostly on and only on microfluidic products, glass solutions. We have our own glasswork, so all the glasswork you actually see is produced in-house. We have Particle Works, who's basically few scientists who actually work on engineering nanoparticles as they are needed by customers. And we have Dolomite Bio, which is a specific biology use of the microfluidics for single cell research. So to get what we will cover in next 40-45 minutes. So I did the introduction. We'll actually talk a little bit about process safety fundamentals. We'll talk about calorimetry in general and the challenges of heat measurement. Then we will focus more on a reaction calorimetry, its first principles and overview, what data can it provide and how it can help us. We'll talk shortly about a few examples, how it can be helpful, sum everything up, and we'll have a time for your questions in the end of the session. So I would like to point out this is meant as an introductory session to basically give people idea where the calorimetry and the reaction calorimetry actually fits in a process safety and process development. So some of you who are more experienced in a subject may find it a little bit too general, but we need to make sure that all our attendees actually have a good understanding before we move in other webinars into more detailed subjects. So we will have a quick poll shown. Please, if you can spend 30 seconds, what level of experience with calorimetry or process development do you have? Okay, so we have the results in, so we have mostly that people have read about the subject. So hopefully this session will be very informative for you. And it's actually a very good indication for future webinars, how much you focus. So let's get into the topic. So first of all, I want to start about the fundamentals of process development and the safety of chemical reactions. Because the process development and process safety is very, very broad and a very detailed subject with lots of legislation and a lot of things. We could actually spend a few hours talking about it. So we will actually simplify it down, not to get overwhelmed with too much information and focus solely on the safety of the chemical reactions. Because in the end, the whole process safety is a big cooperation of not only scientists in the lab and chemical engineers in a plant, but also management, public relations with the local communities. All of this actually needs to be taken into account, and this is literally out of our scope. So we can actually quite easily simplify the process development into 5 steps. It's very simplified, but it will actually perfectly demonstrate what we need to focus on. So yeah, as I said, 5 steps. First, we need to make sure that we know what we actually want to produce. The second step is we need to figure out how we actually going to make the product. The next step would be to make sure that we can actually create a product on a small scale as efficiently and as safely as possible. Afterwards, when we're happy, we can move on to scale up the production. So we would move to so-called kilo lab or pilot plant, which would be a small proof of concept production of our chemical. And the last step, obviously, is the production. So we would probably have a specialized production line creating big batches of the product. So we can actually maximize everything which we really strive for. So we simplified it 5 simple steps, but there are quite a few challenges, including in each of the steps. So what kind of questions can we actually ask? So the first one is really straightforward. What do we want to produce? So when we know the answer, we'll probably get the idea to the chemists who will have to figure out the synthesis path of the desired product. So they will basically design the process. Usually it will be multi-step process of several reactions. We need to figure out what are the properties of the materials used. Are they stable? Are they safe to use? And we also need to figure out what are the kinetics of the process to make sure we can actually utilize the process to run as efficiently as possible. In the next step, in optimization, basically we optimize the synthetic route that was given to us. So how can we run the process efficiently and safely? We can determine what are the process control parameters. So how can we actually make sure that we are in control over all the different aspects of chemical production, and we can actually optimize temperature amps, work-off times, dosing profiles, all those important things which actually make sure that our process is good. When we are happy, we can then move to the pilot kilo lab or pilot plant. So the main questions there are a little bit different because the optimization has been done. We basically need to confirm that we can actually, in a stepwise, increase the scale of production and still keep very high safety margins. And if we are able to actually keep control of the process at higher scale, which can be a very, very challenging thing. We will actually touch on that a little bit later. And of course, during the scaling up, we actually also need to look on a failure scenarios. So are we able to minimize risk if something goes wrong? And in production, quite different challenges actually need to be addressed. So we need to define standard operation procedures. So actually the technicians who are operating the plant know what to do routinely and know what to do if something happens. We need to note all the changes to the process and obviously have a quality control so we can actually make sure that we are producing what we want and with the yields we are actually striving for. So it looks like a fairly straightforward process, but it's a little bit more complicated. So if we actually look at the development timeline, we actually added a few things because it's really a continuous process, because rarely the steps synthesis optimization will happen that we have a first synthetic route which is efficient enough and safe enough to do. So usually from the optimization step, the workflow would return back to synthesis to find a different, for example, more efficient or more safer way to create our product. Or if we found out we have some reactive intermediates which could be potentially dangerous, we need to find out a different way how to create things. So I put a little divide in the middle because it's not as a rule of thumb because it depends on the size of a company. So usually the first 3 steps will be done by chemists. The optimization step will be a mix of chemists and chemical engineers, whether the scaling up and production will usually be handled by chemical engineers. But depending on the size of a site, it can be one person or it can be actually quite a few departments working in close cooperation. And as you can see from the production, we can actually return back to optimization. So if we on a production scale actually find out, okay, the yields, we are not really satisfied with them, you can actually return to optimization. For example, if you have a catalytic reactions, find a different kind of catalyst and re-optimize the process. Even if it's been running for years safely, we can actually make sure that we are getting as best results while keeping a high safety margin still. So what is the history? It's, I think, an important aspect to have a look at. So the process safety itself is a lot older because I think the kind of a comprehensive process safety program was introduced in DuPont Gunpowder Works in 1802. But on a strictly chemical way, one of the best examples is actually production of the nitroglycerin by Alfred Nobel. So we have actually a nice illustration of an operator sitting next to the reactor vessel. And the point was a very large-scale production of nitroglycerin, because Alfred Nobel, as everybody knows, invented the dynamite, and he needed a reliable source of nitroglycerin to manufacture the explosive. And the synthesis of nitroglycerin on its own is quite a dangerous process by its nature, and especially if we took into account in 1860s, because it's done by mixing fuming nitric acid and sulfuric acid with glycerin at fairly constant temperature of 25 degrees. The problem is those additions are very exothermic. So basically the operator sitting next to the vessel was operating valves to make sure the temperature wouldn't go over the margin of 25 degrees. So, and you can actually see on the picture one of the first safety implementations, because if you look at the operator, he's sitting on a one-leg stool. Because as you can imagine, watching a thermometer all day long while operating the valves isn't really the most enjoyable thing to do. If the operator would actually doze off, he would fall off the chair, keeping him awake, and still make sure that if something goes wrong, he would actually still have a time to escape. So that was kind of a first level failsafe. There was also a catastrophic scenario failsafe, because the reactor vessels were designed in a way, if the onset of the decomposition or thermal runaway was reached, the operator could shut down the dosing feeds and dump the reactor tank into the drawn-out tank, neutralizing the regions, giving him enough time to actually run away and minimize the risk to the property, the operator, and the surrounding community. So it's really, the process safety is about understanding the thermochemical data. So if we actually move into more recent things, what can go wrong? So we have two just illustration photos here, because we won't talk about those accidents in detail. But the one on the left is Opal, now Ludwigshafen, very huge explosion of ammonium nitrate in 1921, which was probably one of the biggest chemical plant explosions to date, really, because I believe the fatality rate was about 500, massive property and everything. The interesting thing about this accident is that they actually used dynamite to break down the pile of the ammonium nitrate, which, to be honest, in today's understanding, could be seen as a quite dangerous thing to do. The other picture is from Flixborough, from UK, from 1974. And there was, again, quite a big misunderstanding of the thermochemical properties of the production site. I think this was actually a production of cyclohexane in a cascade of batch reactors, but they found out that one of the vessels actually wasn't up to the job, so they bypassed it with a piping of different size than it was actually designed for, leading to reagent accumulation and actually resulting in a very big explosion. But those incidents actually happened before we actually had a means to determine the critical safety factors. It was way before the reaction calorimeters were available commercially. But we will look at a fairly recent incident in Jacksonville, Florida, which happened in 2007, so just 11 years ago. So it was a very, very big explosion caused by the thermal runaway because of the cooling failure of the reactor. So they were producing a dye, which is used in a petrol industry, which was a batch process. So the reactor itself was 2,500 gallon production scale reactor, and the reaction was initiated by heating up the mixture up to 100 degrees. So one of the regions, the sodium metal, would liquefy, and heating was then controlled up to 150 degrees, where the heating was shut down because the reaction itself actually produced enough heat to be self-sustaining, and only cooling, only a cooling water would be injected into the jacket in an evaporative cooling to make sure everything is under control. But what happened when the reactor, it was manually controlled, it's an important thing to say as well. At 182 degrees, the operator decided that the temperature is a little bit too high, and he tried to commence the cooling. However, the cooling failed. So what was the result? After 10 minutes, the ongoing decomposition reaction in a reactor actually increased the pressure and the temperature beyond any limit. So actually the burst disk and the pressure relief device actually opened, but it wasn't designed for such a flows through it. And the witnesses actually said there was a jet engine-like sound for a few minutes before a huge explosion was heard. And the investigation afterwards actually estimate that the explosion yield was 3/4 of a ton of TNT. So what were the causes? So usually these kind of incidents have a kind of a cascade of the problems. The main problem here was a misunderstanding of the thermochemistry behind the process. Because if you recall the diagram of process development, we had a look. They basically skipped from 1 liter, basically figuring the synthetic way reactor, all the way then to 2,500 gallon reactor to save costs. Another thing that needs to be taken into account was a rather poor reaction vessel design. It was rather simple, and it had too many single point failures, especially on a cooling system, which failed. So afterwards it failed. They had no way how to actually make sure that the system can be controlled again. Another thing was inadequate reactor pressure venting. So it had a burst disk, and it would be able to vent the pressure and nothing would happen, but it was set up for too high pressure. So actually the pressure and temperature increased so much that when it burst, it wasn't able to vent all the overpressure out, leading to explosion. So the fundamental poor understanding of the thermochemistry, because they did some preliminary screening studies and they calculated what should happen, but the secondary reaction or the decomposition of the thermal runaway was way more energetic than they have anticipated and actually tested for. So what was the aftermath? So for the people on site, including the plant owner and the chief engineer who are trying to keep the process under control, 32 people injured in a near vicinity of the site, and massive damages to the property around the plant. The conclusion was that American Institute of Chemical Engineers actually introduced mandatory reactive hazard awareness courses to chemical curriculum at universities, because it was found out it usually just mentioned, but no deeper understanding is really required. So if you look at the pictures here, so the left picture actually shows the agitator shaft of the reactor, which was found, I believe, 3 miles away from the site, embedded in a sidewalk, concrete sidewalk. And on the right picture, we can actually see the remnants of the ruptured vessel. So you can actually imagine what it probably would be like. So if you look at it like this, why is it important to perform calorimetric studies and understand the kinetics and the thermochemistry behind our process? So yeah, we need to understand the kinetics to make sure we know what part of the reaction is actually taking part. We can actually make sure that the process can be run safely under most of the circumstances. And if it can't be guaranteed, we can actually figure out the standard operating procedures and emergency systems to make sure we can control and minimize the risks if some failure would occur. We can actually optimize the processes that are already run on production scale. So to optimize yields, we have a new, for example, we could have a new supply of catalyst, so we can actually figure out if it's going to be better or not. And we can even use it to understand the non-reaction side of the processes, so safe storages, shelf life, and many different aspects we can use it for. So next section, calorimetry overview in general. There are a few challenges that we actually need to address. And the first and the major one for calorimetry and thermochemistry really is the heat measurement. So there are 5 major facts about heat or energy that we need to take into account. So we cannot directly measure heat. There isn't a device that would stick into something and tell you what is the energy actually stored inside, because it's a function of the internal energy. We can only measure its difference over time or temperature gradients. Also, we cannot contain the heat because it will always try to equilibrate with its surroundings. If we have some heat losses, they will be usually localized depending on the heat transfer properties. And the most challenging part is the heat transfer may actually change over time. So for example, if we take into account of the chemical reactor, if our product will change composition, the heat transfer properties will change. So if you look at the picture on the left, we have an IR picture of a house, and you can actually see where the heat losses are occurring. And this kind of a principle, because you may say, oh, it's very challenging, we can actually use those 5 facts to actually measure heat quite accurately, because we can direct the heat in a path we can actually measure. So that's a function of most of the reaction calorimeters and calorimeters alike. So we have different calorimetry solutions, and we will talk about them in a moment. But a very important fact now is to have a look in the history, because people usually don't really realize how important calorimetry was for the development of modern understanding of chemistry and thermodynamics. So the foundations, believe it or not, were actually devised in the middle of 18th century by Scottish physicist Joseph Black, who is considered the founder of calorimetry, because he was the first one to recognize the difference between heat and the temperature, which at the time was quite an undertaking. But he did most of the theoretical work, and he had no means to confirm his hypothesis, which was done by a very famous French chemist, Antoine Lavoisier, who is often considered the father of the modern chemistry, because he built with his quite famous colleague Pierre Simon Laplace the first device to measure heat, or measure heat transfer, the calorimeter, which comes from Latin calor, the heat, and Greek metron, which is to measure. And he based the design around the calculations and discoveries of Joseph Black. And the device allowed for measurements of heat involved in various chemical changes. So basically, it works like the typical ice styrofoam calorimeter most of us actually used in school. So he had a container filled with ice. He had a chemical reaction going around it, and by amount of ice that actually melted, he was able to quantify the amount of energy that was involved in a change. And the interesting fact is that first experiment he did, he actually used the heat from guinea pig's respiration to melt snow in his apparatus, showing that the respiratory exchange is actually oxidation, combustion, similar to candle burning, which was a breakthrough at the time at 1780. And basically those experiments are very important in a field of thermodynamics and modern understanding of chemistry, because it laid the foundations for formulation of the first law of thermodynamics later in the 19th century. So, but if you're a little bit familiar with the calorimetry or calorimeters, there are actually quite few different types. And if we are talking about process development and safety, not all are actually used. So I prepared a quick overview of the different calorimeters that are available. That's obviously not all of them, but there are 4 major groups. So we have bomb calorimeters, microcalorimeters, adiabatic calorimeters, and reaction calorimeters. So the first one, the bomb calorimeters, are still basically using the similar principle as Lavoisier used in his calorimeter in 1782. They are used mainly for determination of heat of combustion. So we would load the bomb, which is usually stainless steel vessel, able to withstand high pressures and high temperatures. And we would ignite the sample inside. It would heat up the vessel, which in turn would heat up the water, measuring the difference between temperature, knowing all the parameters on heat capacities. We can actually quantify the energy of the combustion, usually used, for example, for energy density of a coal in power plants. But that kind of a calorimeter isn't usually used in a process development. The other 3 are used very frequently and usually together. So we have a microcalorimeters. They are also called the differential scanning calorimeters. They are very simple and very effective technique to assess stability and properties of substances, such as their heat capacity, their melting points, the energy needs for melting, and decomposition. And they are very quick to be used. Then we have adiabatic calorimeters, which are used to assess decomposition and undesired reactions. So basically they are used to assess a situation when a failure would occur, so thermal runaways and failure of cooling similar things like that. And finally, we have reaction calorimeters. So we actually have an example here, which is our Syrris Atlas calorimeter, which is basically used to simulate the plant conditions as best as possible. So, and it's basically a jacketed reactor that will allow us on a small scale simulate what will be happening in a big production scale, with provisions to give us the heat transfer measurements and everything. So we will touch on those a little bit further in the session. So the first group, the microcalorimeters or differential scanning calorimeters, they are very simple devices. We have two crucibles, one loaded with sample, the other one is blank, and basically we will heat up linearly both crucibles and basically measure the heat generated inside of the crucibles. And it's differential because we are actually comparing the blank one with the sample one. And it's ideal tool for preliminary screening studies because we require very small amount of the sample, usually it's micrograms. The experiments are very fast, and what data can it give us? So it's usually quantitative energy data. So we have with a small data, small sample, it's very quick to perform, and we can actually get information that we can actually predict the behaviors of compounds and mixtures at higher temperatures. But it has its limitations. The crucibles are very small. The samples cannot be stirred. There are usually no pressure monitoring available, and we are not able to dose into the crucibles as well. And the typical thermogram you can actually see on the right side of your screen. So we have actually two events on the example. So the left one is actually endothermic effect of melting of the solid substance in the sample crucible. And the peak on the right, the broad peak, is actually onset and actual decomposition of the sample. So you can see this is the kind of a data we are able to do with a differential scanning calorimetry, but it lacks all necessary information to do the proper safety studies. So that's why I mentioned we need all of those the combination of the three to get a comprehensive information. So the another group are adiabatic calorimeters, which are very important in process development. They are specialized instruments assessing the most dangerous scenarios. It works on an adiabatic principle. So basically, if you have an exothermic event inside of the reactor vessel, it will work on a principle that all the heat that is generated by the reaction is actually contained, which will result in temperature increase. And those devices are usually very pressure resistant and can actually handle a rather big temperature ramps. So they are usually able to cope with very high temperature changes actually there are examples in the world that can actually heat up with the ramps of up to 200,000 degrees per minute and can handle pressures. So they are ideal tool for investigating the chemical or thermal runaways of the processes. So, and because the sample volume is bigger, it's in a scale of milliliters, we can actually make sure that we can actually stir the samples if needed. We actually get a pressure data as well. But usually the experiments are longer than a DSC, so it's a good complementary thing. And if you look at the mode of operation, so the typical mode of operation of adiabatic calorimeter is a heat, wait, and surge. So it will work, if you look at a thermogram, in a staircase kind of a way, where it will heat up by given amount, wait for given time at isothermal conditions, and then surge to basically search for any changes in the temperature. If it doesn't fit in the margin, it will continue into next step until it can detect there is some thermal event happening in a crucible. Then it will switch to adiabatic mode and record the whole heat release during the decomposition in the vessel. And the last group, very important in the process design, are the reaction calorimeters. So those are devices to simulate the plant operation as closely as possible on a small scale to make sure that we can actually control the process on a small scale quite easily, often used with processes that we are not really sure how they will perform. So they are designed to allow controlled addition of reactants, different stereogeometries to make sure to match as closely as possible the production scale. They will usually have higher volumes compared to the screening methods, the DSC or the adiabatic calorimeters, usually from 250 milliliters up to 2 liters. They have provisions for capturing the thermal data. So if you think about it, it's not really usable for safety studies, but we can actually find the kinetics, different reaction paths, and it will allow us to further optimize the process to run as efficiently as possible. And reaction calorimeters are generally used to investigate a desired reaction, so the process we actually want to follow, which will create our product, in comparison with the microcalorimeters or adiabatic ones, which are mostly used for undesired reactions or just the screening studies. So those are the main types of calorimeters. So if we go back to our schematic, where do they fit? So I actually removed the production scale because we wouldn't use calorimetry on a production scale. So during the first 3 phases, we would use the screening methods as the DSC, really to identify the physical properties of our compounds, regions, their heat capacity, their decomposition temperature, and basically their behavior at higher temperatures. During the synthesis and optimization, we can actually start using reaction calorimetry. So we can scale up our process to the scale of up to 2 liters and actually start mimicking the production plant. So we can have a controlled dosing, controlled stirring, and everything. And usually we will optimize several times. And when we are actually starting to be happy with our process, we can actually take the adiabatic calorimetry in the process as well, which basically we can study the process we are optimizing, how it will perform at the extreme. So during the thermal runaways, during the cooling failures, during the stirring failures. So let us focus on the reaction calorimetry now and what is its place in the process development, which we just shown. Because it's compared to calorimetry, it's a fairly new method because the first commercial availability of reaction calorimetry was, I believe, in 1986. But the introduction of such systems allowed for staged process development, so the stepwise approach that I showed on previous slides. And as the process grows in a scale, we can still keep pace with it and make sure everything will be under control. And using calorimeters, are not really restricted to this. We can actually even predict what will happen if we have enough data. And as I mentioned before, we can actually use it for processes we are quite happy with to improve them even further. So let us look at a quick history on a reaction calorimetry. So what it actually is. So the first, an original idea came from Switzerland, from Willy Regenas in 1970s, and which wasn't originally for safety studies because he basically created a jacketed reactor device which was used for determination of thermal efficiency of the chemical reactions, so to quantify the heat of reaction and the enthalpy. But it found a way very quickly into safety studies and the process development. So there are 2 really important rules that we need to follow. So the first general rule is we want to work in a small scale. So as I mentioned, up to 2 liters. It's very important because at a small scale, we are able to handle, for example, extreme exotherms very, very easily because the surface to volume ratio, for example, on this vessel and, for example, 50 or 100 liter vessel is very different and it's very hard to control bigger size processes. So this is basically can be used as a kind of a playground for the chemists to make sure they understand what is happening and what is the energy profile of our reaction. And the second important thing under realistic process conditions. So we will try to actually match the vessel geometry, the stirring geometry, the stirring speed, the dosing ramps with the actual design process. So we can actually simulate it on a safe side to make sure nothing will happen. So what are the topics in reaction calorimetry? What we will cover? Some applications and different methods, how we can actually measure heat in chemical reactors, when it should be performed, what data can we get from typical reaction calorimetry experiments, and interpretation of data. So examples, how reaction colorimetry can actually help you, even though, for example, re-optimization of the process, using examples, using reduction agents. So the applications. This is really just a general overview, because obviously there are quite few things that can be done, even though they are set here differently. So mostly they are used for semi-batch reactions. So difference between batch reactions and semi-batch. Batch reaction is that we actually dose all the regions inside of the vessel, and usually the process is initiated by raising a temperature or adding a catalyst, which can be quite challenging because of the principles how typical reaction calorimeters work. But there are devices such as the chemisense calorimeter you can see on a picture, and we have the reactor here actually, which can actually handle pure batch reactions and even continuous flow reactions. So there have been papers published regarding this. Another prerequisite is that we are really limited to mobile media only, so liquid ones. Usually working with solids only or highly viscous media can be very difficult to assess. It always also comes down, It also comes down to the measuring principles, which we'll touch on the next slide. And as we are trying to actually make sure that we are mimicking the production line, the production will usually run under reflux conditions. So we can maximize the efficiency. So higher temperature means faster reactions. Faster reactions means more product, means management's happy. And obviously, we will run also at elevated pressure usually, because then we can raise the boiling point of our solvents in the reactor, allowing to boost the reaction even further. So touching on the techniques. So we mentioned that heat can't be directly measured. So we are actually measuring the secondary heat transfer. So first thing we need to mention is the difference between primary and a secondary heat transfer. So we have so the primary heat transfer is actually inside the reactor, inside the reacting mass. The secondary heat transfer is actually the reaction mass transferring its heat to its surrounding. So in case of this reaction calorimeter, it would be transferring the heat from the vessel into the cooling jacket, and we would be determining the reaction power by the change of the temperature in the jacket and their difference. So there are three main techniques. It's a heat flow calorimetry, which was basically the one that Willy Regenas actually introduced. The true heat flow calorimetry, which is basically a very novel approach, which actually removes most of the disadvantages of a heat flow calorimetry. Heat balance calorimetry and power compensation calorimetry, which is a special case of the heat flow calorimetry. And we will usually run under isothermal or isoparabolic conditions to make sure that we can mimic the plant as close as possible. Since we have a limited time for this webinar, actually the technical talk about the methods, their pros and cons is planned for next webinar session, which will be held in January. So please stay tuned. So what data can we actually obtain with the reaction calorimetry? That's a quite important question to be asked. So we will actually look into four really most important ones, which is obviously the heat of reaction or the enthalpy change. So the definition is quite simple. It's amount of energy or heat released or absorbed by chemical reaction. So released, it's exothermic reaction. Absorbed, it would be endothermic reaction. And it's actually quite simple, because since we can't measure the enthalpy directly, we can actually only measure the change. So it's usually the final enthalpy minus the initial enthalpy. That's a very simple way to put it. For process development, the preferred way to report it is in a specific heat of reaction, so in kilojoules per kilogram, because it's very easily scalable at a different scale of the reactors, because it will be same in a half-liter reactor and same in a 100-liter reactor. There is a one quirk with most of the reaction calorimeters though, because as I guess quite a few know from thermodynamics, endothermic reactions have a positive sign and exothermic have a negative sign. Most of the commercially available calorimeters will actually report it the other way around, which is a bit counterintuitive. But it actually makes sense in a way, because calorimeters will report all effects that actually lead to temperature increase, meaning exothermic effects, as a positive. And we can actually calculate the enthalpy change quite easily, theoretically, from enthalpies of formation if we know our process really well. However, it is always advisable to measure the heat of reaction under realistic conditions to basically confirm the calculations. Another important thing is heat capacity, so amount of energy needed to raise the reaction mixture temperature by 1 Kelvin. This is actually quite easily measurable during the initial screening test by DSC, but the reaction calorimeters will give us the possibility to actually measure it continuously. So the specific heat capacity, again, kilojoules per kilogram per Kelvin, is very widely used because we can use it and it's directly scalable. And it actually allows us to calculate vital safety parameters, which one of the most vital one is adiabatic temperature rise, which we talk about now. So it's a thing with temperature rise when conditions change to adiabatic. So what happens if the conditions change to adiabatic? So as I mentioned it with the adiabatic calorimeters, basically most of the heat that is released by the reaction will be contained inside, resulting in a temperature increase. Typical example where the typical reactor can enter this kind of a mode is where the cooling failure occurs. And it's calculated from the specific heat of reaction and specific heat capacity of the reaction mixture. And it's one of the major indicators about the criticality of the process. We'll touch on that a little bit later. And the last very important one is reaction accumulation. Because in percent, we can actually give us instantaneous percentage of non-converted reactants. So we have two scenarios, fast and slow reactions. So fast reactions are usually very desirable because, for example, if we dose some region inside of a reactor, it would immediately react and we have an immediate response from the reacting systems. So we can actually control the rate of heating by limiting the feed rate of the region. But that's unfortunately not always the case, because if we encounter slow reactions and we add too fast, we will actually have unreacted regions inside of the vessel. We literally have no control. We can't really do anything while it's inside. So there could be even a situation that the kinetics are such that we actually have to add quite a lot of region before our reaction takes place. And the rule of thumb that processes with high level of accumulation can be more hazardous. And because even if we actually stop the dosing, we have still quite a lot of unreacted regions which will still release the heat, which can lead to potential thermal runaway. So to understand a little bit more, I have this small diagram. So if you look at it, there are 3 lines. So the black one is the dosed amount. So you can see, and if we talk about the fast reaction first, on the onset of dosing, we have a reaction power increasing, and as we stop it, it will decline quite fast back to the baseline. With the slow reaction, you can see when we stop the feed, it's basically just about when the reaction power reaches maximum. And even if we stop the feed, it will take a long time for the reaction to actually work off back to the baseline, because we have a large amount of reactants present inside the reactors. We can't literally do anything about unless we use some quenching technique. So what are the other things that we can actually read from the reaction calorimetry? Obviously, there are a lot more we can do, but these are really the basic ones. So as a power output, we can actually describe physical characteristics and their changes, for example, crystallizations. We can actually measure gas generation in our process if it's needed, and we can actually check the species formation as well. So what can we actually get? So we can actually make decisions to make sure our process is safe. So for example, we can make sure that even during the cooling failure, the boiling conditions wouldn't be reached if it's undesirable, which usually is, unless it's a reflux process. and we can actually make sure that the secondary reaction or decomposition, the thermal runaway temperature, isn't actually reached even during failure scenarios. It will give us a power output, so we can actually calculate the cooling power needed to run our plant safely and prepare for construction of such, and give us accumulation data, so we can actually optimize the dosing feeds to keep the reaction under control under all circumstances. And we can quite easily also evaluate the use of catalysts and different types of catalysts. So the main message is the efficiency of the process can be fine-tuned very effectively using the reaction calorimetry data, even for the processes which have been running for years without a problem. But that is not all, because the advances in technology and sensors allows us methods to be implemented straight to the reaction calorimeters. So we can actually have a in situ analytics, so we can have IR probes monitoring our regions. We can have a Raman spectroscopy. If we have for example, crystallization process, we can monitor particle sizing and its distribution. We can monitor pH and control. We can have a real-time sampling using autosamplers, or we can even have an online GCMS analysis of headspace gases if they are being generated. And on a picture, you can actually see a thermogram from reaction calorimeter, actually this one, which was acetic anhydride, and you can see that the purple line is the actual enthalpy of the process, whereas the blue and the red curves are the signals from IR spectrometer, which basically confirms the conversion of the reactants in the reactor. So that was basically the desired reactions. So what will happen if you have a process deviations? So the green line is basically what typical process would be. So we heat up to the process temperature, everything is running. When we're done, it will decline back. We have our product. So what happens, for example, if you have a cooling failure? Then the yellow line actually takes place, because we will enter adiabatic conditions, so all the reaction is still going, temperature will increase even further. It's called a deviation temperature. But in a case that our process actually has been poorly designed, or the decomposition reaction actually is very close to the process temperature, we can reach the thermal runaway, which will result usually in a reactor failure. So the typical thing to be done really with the process is the criticality assessment. So we can actually quantify any process in one of the 5 groups, depending really on 4 major indicators. And there are very extensive guidelines how to actually, if you find out that your process, for example, is criticality hazard 4, how to actually make sure to move it back, because criticality steps 1 and 2 are usually considered safe. So we need 4 values to actually do the proper quantification in this case. So we need to know the decomposition temperature or its onset, which is the orange field on the diagram on the right. We need to know the boiling point of our reaction mixture, which is the blue point. We need to know the process temperature, so the temperature our process is designed to run. And we need to do the maximum temperature of the synthesis reaction, which is the process temperature we're running at, and the temperature of the adiabatic rise if the cooling would fail. And depending on how those values are actually organized, we can actually see how critical our process is. So there's a lot of literature on the internet from different societies. I don't really want to go into too much detail, because it's probably a material for another 2 or 3 webinars. So potential process deviations, so I just listed some of them. Obviously, the most frequent one is the last one, is the system failures or human factor error. Well, what can be the human factor? We can have wrong reactants put into the vessel. We can, if you have a multiple regions, wrong dosing order. We can actually start addition at the wrong temperature. We actually have a wrong flow rate of the reactions, which can all lead to potentially dangerous situations. So those are the things we can actually identify and simulate using the reaction calorimetry, or combination, or in conjunction with the adiabatic calorimetry. So we are now reaching the place when we will look at the examples. So I have 2 examples, which were reduction using solid metal hydrides. And Just a simple fact, semi-batch process, heterogeneous reaction. So we have a reaction mixture and we add our reducing agent inside of the vessel. So we basically are agitating a slurry while the reduction is taking place. So the temperature of the process is critical in this phase because it will initiate the reduction. So if the temperature is too low and we add the reducing agent, we have a high amount of accumulation because it will take some time before the reduction starts and the process keeps running. So as this process was designed, no deviations were actually found during the process development, even with the reaction calorimeters. So they proceeded to scale up to 100 reactors, and thermal runaway has actually occurred. So the obvious question will be why, because it didn't show earlier. So they actually used the data from the scale-up reactor, simulated the runaway with the information from 100-liter reactor, and they found a simple fix. Just raise the reaction mixture temperature by 10 degrees. Because with a higher temperature, if you add the reducing agent, the reaction is initiated immediately, so which led to very, very, very lower levels of accumulation of the hydride inside of the reactor, keeping the batch temperature at acceptable levels and controllable levels. So the conclusion from this example is very simple. You can use the reaction calorimetry to understand and redesign even if something goes wrong during the scale-up. The second example is a reducing agent. Again, a little bit different situation though. So again, heterogeneous reaction, solid addition of the reagent, and they actually ran the process very, very successfully for 20 times in a pilot lab on a bigger scale. So they actually decided, all right, it's perfect. We'll proceed to another step in our production, which was quenching the sample with the aqueous sulfuric acid. And as they did it, the plant was immediately filled with the smell of rotten eggs after quenching. So what could go wrong? What did went wrong? So after they cleaned up the lab, they actually found out that the agitator in the reactor had corroded off and fell off the shaft. But since the shaft was still rotating, it still indicated the correct speed. The lack of stirring led to the high level of accumulation of the reducing agent. So it didn't react altogether as they were used to. So after adding the quenching reagent, the accumulated reactant actually reduced the water from the aqueous solution of the sulfuric acid to hydrogen gas that subsequently reacted with the sulfuric acid, forming hydrogen sulfide, resulting in the smell inside of a plant. So they actually took this experiment to reaction calorimeter and they confirmed that the reduction of water with the forming of hydrogen sulfide is a preferred path. So for their process development, they needed to make sure, and it's essential to make sure all of the reducing agent is actually converted before proceeding to the quenching step. So just to few conclusions. So is it really necessary to do the calorimetric studies? Well, it is. Reaction calorimetry can provide all the data you could possibly need to understand the reaction you're trying to perform. And if you have a multi-step process, you should really pay a lot of attention to every step that you're not really sure how it will go and how it will behave. You can actually simulate the what-if scenarios, and if you have some problems, you can actually recreate them, and it will give you the provisions to understand what went wrong. And basically, the real message is scaling up without knowledge of the thermochemistry of your process can lead to potentially hazardous situations. And there was quite a lot historically and even quite recent incidents reported because of a lack of understanding of the thermochemical parameters of the process. So I know we overrun a little. So let's do the summary. So we covered the basics of the process development and the process safety fundamentals. We have looked at different types of calorimeters and the difficulties and challenges of heat measurements. We looked in a very, very introductory way on the reaction calorimetry, its first principles and overview, and we have looked at examples how it can be actually used to understand the process better. So as we mentioned, it's really introduction. We plan to go a lot more technical in the next webinar, which basically will focus on the reaction calorimetry and the different techniques, as I mentioned, the heat flow calorimetry, the true heat flow calorimetry, and the heat balance calorimetry, more in detail, explaining all the pros and cons of such. So we are reaching the question time. So I would like to ask you, please ask your questions on your GoToWebinar screen. There is a questions tab. Please submit them, and we will try to answer some of them. But don't worry, we will actually answer all the questions, even those we actually can't do here live. So I'll let you have 1 or 2 minutes to actually submit your questions. Okay, so we have some questions coming in. So I'll ask my colleague to actually read them out for me.
Okay, so the first question, what types of calorimeters are used for typical safety studies?
Okay, so let me repeat it because my colleague doesn't have a microphone. So what kind of calorimeters will be used for safety studies? So usually you need a combination of the screening method and the reaction calorimeter. So, but usually all three methods, the microcalorimeters for the initial screening, the adiabatic calorimeters for the failure mode scenarios, and the reaction calorimeters to optimize and understand your desirable reactions will be used. But usually you need some combination of the two to give you a perfect understanding of your process.
Okay. Someone's commented that they've noticed reaction calorimeters usually have quite small vessels. Why is that?
I actually mentioned it. Sorry. So we have a question: why the reaction calorimeter have usually smaller vessels? I actually mentioned that before, because on a smaller scale, we can actually deliver easily a lot more cooling power. So we are actually able to control the exotherms on a small scale a lot more easily than, let's say, in 20 or 50 liter reactors, where we would need a lot bigger cooling power to actually keep the conditions under control. So that's the reason. Usually the smaller scale, the better. Also depends on the sensitivity of the methods. There's a lot more, and we will actually touch it in the next webinar.
Another one, you mentioned that reaction calorimetry can be conducted in liquid medium only. What about crystallization reactions where a solid phase is formed? What information can reaction calorimetry provide about crystallization in aqueous conditions?
Okay, so there's a question about, because we mentioned it's possible, it's desirable to do the calorimetry in a liquid media, and is it possible to do calorimetry, crystallization studies? It's very well possible. It really depends, because even crystallization is a thermal event, because we need energy to form the crystals. So it really depends how sensitive your device is. So there are calorimeters, reaction calorimeters, which are very sensitive and actually aren't affected by the phase change inside them. So you're actually quite easily able to quantify the energy needed for actual forming of the crystals. And as I mentioned, you can actually combine it with methods such as FBRM to actually measure the particle size distribution and their shape really online as your reaction is happening. So I believe that's the simple answer.
And another question, are there any industries where calorimetry is valued more than others?
Well, so are there any industries where calorimetry is more valuable than the others? Really, the major application is the process safety and chemical plants. Really, that's by far the most used place, really, because that was originally why the reaction calorimeters themselves were really used. But I know it's a very important thing, for example, even in biology. For example, you would use the DSC, the microcalorimeters, to actually understand the mechanics, for example, of protein crystallizations, and they I forgot the word. And basically they're breaking down with heat. So actually they have a quite wide biology applications. And if your system is actually sensitive enough, you can actually do calorimetry studies even in a kind of a bioreactors to actually understand the biological processes as well. It all comes down to technique used and the sensitivity of your system. So, so if we have more questions, we will actually answer them privately in an email. One more thing, I know that we didn't really mention our offering, but if you're interested, because this was more on the educational side in our products, please check our website. You'll find a lot of information about our offering in reaction calorimetry, and we are here to help you. So I would like to thank you for your attention and for your time. And one more thing, after we actually stop the broadcast, a survey will pop in on your screen. If you could spend 1 or 2 minutes filling it would be very helpful to get a feedback. How did you like? What did you didn't like? And to help us improve in the future webinars. So thank you again for your attention. We are Syrris. We are making more chemistry possible.